Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to predict the sign of entropy uh, when you have a phase change or something like that. So when you are trying to decide whether or not the sign of the entropy change, if the change is such that you're going from less entropy to more entropy, or from more entropy to less entropy, whether the sign is plus or minus, right? You have to kind of keep in mind about this idea of disorder, right? So one of the easiest ways to think of the change in entropy is to think about, is disorder increasing or decreasing? Is it becoming more orderly or less orderly? Another way to think about it and is to think about it in terms of the spreading out of energy. Where can the energy go? Are there more places to put the energy? Can the energy be spread out a bit more into different places? So, for example, right, you can think of, say, you have a block of ice. Now, the water molecules in a block of ice are pretty ordered, right? They're kind of combined together, they're attracted to each other, they're stuck in place, they can't really move around except for maybe vibrational motion. And so you got an ordered structure there of solid water molecules, in solid water. So one, it's an ordered structure, and two, there's not a lot of places to put the energy. The energy is really contained mostly in vibrational motion. Now, if you melt that water, right, and make it into a liquid, now the water molecules are not as organized. Now they can move around a bit more. You've got more places to put the energy, more states that are available to the molecules, right? So now you have, in addition to vibrational motion, you have translational motion, you have rotational motion. So the energy now can go into these other types of motion. And so there's a spreading out of the energy. And that is also an increase in entropy. So an increase in entropy can be viewed as, a dispersion of energy in the system, a spreading out of energy, or it could be looked at as an increase in the number of states, the microstates. If you read in your textbook, it might talk about microstates. Also, an increase in the amount of disorder. So I'm going to go over a few practice problems to help you see this. And the practice problems are going to gear towards mostly phase changes, and to see how the change in entropy is affected by a phase change. So I talked about water. So I already talked about this in my intro just now. So here I'm talking about gas, but in this way, we're going in the opposite direction. So instead of starting with solid, we're starting with gaseous water molecules. So these are very spread out. They're moving around pretty fast. They've got all this motion. So the spreading out of the energy, right? So if the molecules are spreading out, right, and the molecules have energy, then the energy itself is spreading out. The molecules are taking the energy with them, right? So you can think of it that way. So here we have molecules are spread out. They're moving fast. They got lots of energy. The energy is spread out. Lots of disorder, So in this case, if you were to cool the water down and make it into liquid water instead of water vapor, now the water molecules are much closer together. They're more compact. The energy of the molecules is coming together as the molecules come together, right? So there's not a spreading out of the energy. It's less disordered. So we would expect the delta S here to be negative, right? So what about B? We have carbon dioxide solid. Carbon dioxide solid, if you didn't know, is dry ice. Dry ice, as you are probably familiar with, is that block of what it looks like ice that kind of becomes a gas. And this is where the fog comes from in movie sets and scary houses and things like that, right? So you have your dry ice. That's actually solid carbon dioxide gas, right? It's not a gas, it's solid carbon dioxide. Carbon dioxide is normally a gas, but when you cool it down enough, it becomes a solid. So here we have carbon dioxide molecules in the solid form. Again, very compact, very structured, lots of order, right? Not very much motion. So the energy is kind of not really spread out. So what happens when it becomes a gas? It goes from a solid to a gas. We see this when you have a block of dry ice. You can see the fog coming out, the mist coming off of the block of ice. It's going from a solid directly into the gas. It's like it's passing the 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 liquid phase. So it's passing go. It's passing liquid phase and going straight to gas. And so we call that's called sublimation, when you go from solid directly to gas passing the liquid phase. So here, carbon dioxide as dry ice is becoming gaseous carbon dioxide. So it's spreading out, it's taking energy with it. The energy can go into different places, right? And so in this case, we have, again, an increase in disorder, an increase in the spreading of energy. Energy is spreading out, expanding. And so we would expect the delta S, the entropy change, to be positive in this case. We're increasing entropy. Entropy increases. Disorder increases. The spreading out of the energy increases. The different number of states in which you can put the molecules is increasing, right? Different microstates, if I will. Okay, what about C? Here we have 2 moles of N2O gas, right? So we have 2 moles of N2O gas, and then this is going to be breaking down. This is decomposing into 2 moles of N2 gas and 1 mole of oxygen gas. So here we're increasing the number of moles of molecules, right? So here we have 2 moles of molecules on this side, and here we have a total of 3 moles of molecules. We're increasing the number of molecules, right? Increasing the number of moles of a gas. So when you increase the moles of a gas, you're increasing the amount of energy being dispersed. You're increasing the disorder, right? More molecules means more disorder. And they're all gaseous. There's no difference here and here. This is gaseous, so there's no phase change. But there is a change in the number of molecules. If you change the number of molecules, you're changing the complexity of the system. You're changing the order, the disorder. And so since we're adding more molecules here, this is going to be more disorder. Also, you can think of this in terms of microstates. More particles means more microstates that can be arranged in different ways, right? You can think of this in terms of the energy, right? So the energy now is being spread out or divided into different particles here. So again, spreading out of energy. So all of this helps us to understand that in this situation here, we would expect entropy to increase. So delta S is going to be positive again. Okay, here we have liquid going to gas. Here we had gas going to liquid, and we said before that would be a delta S being negative, a decrease in entropy. But the opposite here, we're going from liquid to gas. Obviously, if we're doing the opposite, if we're going into the opposite direction, then we would expect the opposite result. So in this case, delta S, the entropy would increase, and that makes sense because again, we're going from tightly packed or relatively packed molecules. They're not solid, they're not stuck in place, but they're very close together, more close together than as in a gas. And so they're going to be moving around. They're closer together, not as much disorder. The energy's not as spread out, it's more compact. And so this is going to go from more compact to more spread out. So here the molecules are spread out, taking their energy with them. And again, more disordered, more places, more microstates to keep in mind. And so again, we would say that this is going to be a delta S. Here it's increasing. So the delta S, the entropy change is positive. It's increasing entropy. Here we have iodine. So we have I2 molecules. I2 is one of those diatomic molecules. This is an element that exists as a molecule. There's about 7, 8, 9, about 9 of those. So here we have iodine molecules going from gas to solid. So again, we're going from spread out molecules. Energy is spread out. We have translational motion, we have rotational motion, we have vibrational motion. All of the energy is kind of spread out into those different types of motion. The molecules are spread out, and then we're going into a solid. So the molecules are coming back together, bringing the energy. So the energy is not as spread out. The motion, less motion, right? Because now they're stuck in place, and so the only motion we really have is vibrational, not translational. They can't really move out of place. They're not really going to rotate in place. So less places to put the energy. So the entropy is going to be lower in this. We're decreasing the entropy, so that makes this negative. And then again, for finally, we have our calcium carbonate. Calcium carbonate is a solid. Over time, it will break apart. It will decompose into calcium oxide, which is a solid. But then we're producing carbon dioxide gas. So we're going from a solid to a solid and a gas. And the gas here, again, spreads out, takes some of that energy with it. So the energy spreading out. Spreading out of energy means an increase in entropy. So going from a solid to a solid and a gas will increase the entropy. So the change in entropy for this one is going to be positive. So that's it. That's how you determine the delta S, the change in the entropy. What is the sign of the change of entropy? If you're increasing entropy, then it's going to be positive. If you're decreasing entropy in the process, it's going to be negative. And so I hope this helps you figure out what the sign of entropy change is. If you found this video useful, then please, by all means, like this video, hit that like button. Also, make sure you subscribe to my channel, hit that notification bell. And when you do, make sure you hit all. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. Let me know if you have any opinions, if you've got suggestions. I would love to hear from you. Thanks for joining me, and have a great day.